Alright, part 5, chapter 5, light and electron configuration. The first part of this was spent going over light, calculation, speed of light, using Planck's constant, and figuring out energy, frequency, and wavelength. So let's work on these calculations first. It says calculate the frequency of light that has a wavelength of, and it gives you the wavelength. So ask yourself, what two variables do I have here in this equation? And then look at your possible equations. We'll give these to you on the test. And figure out which one you need. So over here you need the speed of light one because it's got frequency and wavelength in it. So always, always, always write your formula first, then fill in your numbers underneath each word, or each symbol. So speed of light is c. That should be something that you know, or at least you can look up. 3.0 times 10 to the 8th. And I'm not going to put units on stuff in my problem here because I'm having a hard enough time writing with the pen and it'll make it look too sloppy. But you might want to consider putting units in so you see what cancels out. Alright, now we got a wavelength of 4.9. So we're going to put that over here underneath the wavelength sign. This is lambda for the wavelength. So 4.9 times 10 to the negative 7th, and that's measured in meters. If it's not, you got to change it to meters. Remember, meters in, meters out, never ever put nanometers in there. And if you do have nanometers, convert it. Use dimensional analysis, convert it to meters. Alright, so you're going to be looking for the frequency. So divide through, get frequency alone. This will cancel out. Divide through by 4.9 times 10 to the 7th. That'll cancel. And then frequency ends up being 6.1 times 10 to the 14th. And then for units, we could write per second. Remember, this is how many times a wave goes by in a second. We could also, instead of writing per second with its line, we could just put seconds with a -1. That means the same thing. It means a unit should go on the bottom. Or you could use the unit hertz. That means how many times per second. So I don't care what unit you put on as long as you put on the correct unit. Next one, B. Calculate the wavelength of light that has a frequency of that many hertz. So there's your frequency. Now you have to calculate the wavelength, but you still use the equation that has frequency and wavelength in it. So speed of light is always known. It's 3.0 times 10 to the 8th, and then meters per second. We don't know the wavelength. We're going to solve for that, so I'm going to keep that as my variable. And then my frequency is 5.3 times 10 to the 14th hertz, or how many times per second. Get lambda alone, divide by 5.3 times 10 to the 14th. Do the same thing over here. Divide by 5.3 times 10 to the 14th. And then you end up with wavelength equals 5.7 times 10 to the negative 7th. It should be small. You're talking about the size, the distance between one wave and the next. It's going to be a very, very small number. Remember, exponents that are negative end up between 0 and 1. So this is true. And then ask yourself, what unit do you have? Well, I've said before, meters in, meters out. If you have nanometers, you got to turn it into meters. Or if the question says in nanometers, you have to get meters out and then convert it to nanometers. But these are pretty straightforward. If nothing said, you could just use meters. Alright, C, calculate the energy. So now we have a different equation here. We're dealing with the energy of an emission that has a frequency of. So we're going to use the energy formula up here. So fill in E, that's what we're solving for. H is Planck's constant, and then you're going to plug in your frequency. So we don't know E, that's what the problem's asking. We do know Planck's constant because it's a constant. It's something that you should be familiar with, or at least have in your calculator. 6.63 times 10 to the negative 34th joules seconds. And then you're going to multiply it by the frequency, which is given to you in the problem. 6.43 times 10 to the 14th per second, or second -1, or hertz, whatever you want to use. And this is pretty straightforward. It's just multiply these two and you get the energy. So energy is going to be 4.26 times 10 to the negative 19th. And then energy is measured in joules for now. So we're going to put the J over there, and there's our answer. Finally, it says calculate the energy of an emission that has a wavelength of. So we have a little issue here because the formula for energy is dealing with frequency, not wavelength. So we can use other information that we know first to get the frequency. So we're going to plug in speed of light, 3.0 times 10 to the 8th meters per second. And then we're going to plug in the wavelength, 5.55 times 10 to the negative 7th, that's in meters, and we're going to solve for frequency. Frequency is going to be 5.4 0.41 times 10 to the 14th hertz. There's our frequency. And then we're going to take this number and do a second equation. Energy equals Planck's constant times frequency. So energy is going to be what we're solving for. Planck's constant is 6.63 times 10 to the negative 34th. And then frequency is now this number over here, 5.4 times 10 to the 14th hertz, and then multiply them together, and energy is going to equal 3.59 times 10 to the negative 19th joules. Okay. Alright, last one. Calculate the frequency of an emission that has an energy of. So now we're going to use the energy equation also, since we're given energy. Planck's constant times frequency. We know the energy, 4.60 times 10 to the negative 19th joules, a little bit of energy. And then we're going to plug in Planck's constant, since we know that, 6.63 times 10 to the negative 34th, and we're going to solve for frequency. So get frequency alone, 6.63 times 10 to the negative 34th, divide both sides, and then frequency equals 6.94 times 10 to the 14th, and then it's frequency, so again it's hertz, it's per second, or it's second negative 1. You can decide which one you want to use. You have a ton of practice examples that should be in your notebook. Go back and look over those if these are a little confusing or if you need some more practice. But you should be able to do these on the test. We will give you all of this information up here. Alright, 47 deals with labeling the following diagram. So you're going to have to look at a picture like this and ask yourself, where's the high energy, where's the low energy, where's the high frequency, da-da-da-da. So on this side, we're going to have high frequency. We're going to have low wavelength. Yep, see how short and close together those waves are? And as a result of the high frequency, we're going to have high energy. This side's the opposite. We're going to have low frequency. Not a lot of waves will go by in a second, but we're going to have a very long wavelength. And because of low frequency, we're also going to have low energy. So this is not the side that's going to do damage to you. This is the side where you're going to have your radio, where you're going to have your microwaves, where you're going to have your infrared. Now notice right outside of infrared is the visible spectrum. Here's red, then we have orange, yellow, green, blue, indigo, and then violet. Now right outside violet with a little bit more energy is ultraviolet, and then next to that we have X-rays, and then we have gamma rays. So I would be familiar with that order and be able to make comparisons, which is a higher wavelength, which has a longer frequency, or a higher frequency, which has more energy, and so forth.